everyone, welcome to this video. In this video, we'll be looking at several examples of normal subgroups. The first example here is about a group and let's take its center as ZG, right? Which is, as it forms a subgroup of the group G. So this subgroup here is always a normal subgroup. Why this is so? Because if we take some element small a from the group capital G, and if we take some element say small h from the center of G, by the definition of center of G, it would commute with all the other elements of G, right? So AH would be equal to HA for all A in G. This thing would be true. Then only this element H would be a member of the center of G. Hence, our left coset constructed by the element A and using the subgroup this Z of G is equal to the right coset which is generated by the coset representative A, right? Hence, it forms a normal subgroup. Let's move to the second example here. It is about permutation groups. If you remember the symmetry group, this is a group which takes the set of which is a group consisting of all the permutations. And what are permutations? If you remember permutations, they are functions which map some set S to the set S, where what is S? It consists of all the natural numbers up to the member n, this subscript n, right? So if we take all the permutations of such kind and call that group to be the symmetry group, and if from this group we take the permutations which are even permutations, which could be broken down into even number of transpositions, then we call that group as an alternative group, which we represent by capital A subscript n, right? So we say this alternative group here is a normal subgroup of the symmetry group of permutations. You can verify this thing, and for this particular group I wanted to tell you a thing which we discussed in the previous video. Remember, I told you that AH that is equal to H dash A. If this is there, if we say the left coset is equal to the right coset, right, then it is not always true that H is equal to H dash. This thing I wanted to tell you in this through the help of this example. So let's consider some element from the group which is Sn. Let's take this to be the transposition 1, 2. And let's take some element from the subgroup, the alternating group, right? Let's take a 3 cycle here consisting of the numbers 1, 2, 3. So 1 maps to 2 here, 2 maps to 3 here, 3 maps to 1 here, right? Okay, so now when you calculate this element where you compose this transposition with this 3 cycle, you have this as the result, right? You can check this. Similarly, if you have it reverse, that means you are checking the element for the right coset, you have this 3 cycle composed with this transposition. In that case, you have this as your result. Now you see both of them, they are not equal to each other. Hence, these two are not equal to each other in this case. However, that means they in general has not to be true, because this thing is not true in this case if we take this to be AH is equal to HA. So that means this H and this H has to be different. So let's see what are they in this particular case. So we have already calculated this computation, right? You can pause the video and do it yourself. Then if you instead of taking this 3 cycle 1, 2, 3, you take the 3 cycle 1, 3, 2, what do you have? You have this 3 cycle 1, 3, 2 composed with 1, 2, right? So when you get solve this, you have this as the answer, which is the same as this one, right? They are equal to each other. Hence, if you have AH is equal to H dash A, which is what? It is 1 and 2, 3 in this case, then H is not equal to H dash in this case. So here 1, 2, 3, that is not equal to 1, 3, 2. Hence, this is what we have discussed in the previous video. So here in this case, this alternating group, I am saying that is a symmetry group, that is a normal subgroup of the symmetry group, right? So let's now move on to our next example, example number 3. Now here let's take the group as the dihedral group. Now if you remember what is a dihedral group, it is the symmetry group for n of a polygon, right, having n sides. So here let's take this group. You know what are the members of this group? They are rotations and they are reflections, right? This we have already studied, and if you wanted to go in more detail of this dihedral group, you can check out another playlist based on questions on group theory. There we have details of this dihedral group. Okay, so now we are saying if we take this group, the dihedral group, as our group, then the subgroup of this group, which consists only of the rotations, we say that is normal in this group Dn, right? So Dn consists of both rotations and reflections. However, we take the subgroup, let's call that to be the subgroup H. It only consists of rotations, right? This is given to us. Now we say this H is a normal subgroup of Dn. Let's see how this is there. So here we have two possibilities, either of rotation or of reflection. If we take some element, either it would be rotation or it would be reflection. Let's discuss it for both the cases. So let's first take an element which is a reflection from Dn, right? Another thing, because the subgroup only has rotation, so let's take R from here. So if you take any rotation here in H, for that particular rotation, you would surely have Fr is equal to R inverse F. This thing would always be true in case of dihedral group. You can check the Cayley table and verify it for each element, each rotation, as well as for each reflection. This thing would be true. Hence, the element was this reflection. The element into this would be your left coset, right? F and H. H is your subgroup, and then this would be your right cosets. Both of them, they are equal in this particular case. Now let's take another element which is rotation in Dn. Let's take this one. So let's take rotation in Dn, and let's take rotation in the subgroup because it only has rotations. So in this case, we also have R1 R2 equal to R2 R1. So that means in this case, for any R2, we have the left coset equal to the right cosets. Why this is so? Because any two rotations, they commute within this dihedral group. You can check the Cayley table for this. Hence, we say the left coset here is equal to the right coset, and this is what we wanted to prove here in order to prove that the subgroup of rotations is a normal subgroup of the given dihedral group. So I hope you understood these examples well. Well, that is it for this video. Thank you for watching.